Hello, welcome to the class ECE317 Digital Signal Processing. Today we will start chapter 3, a new chapter, chapter 3, Z transform. Alright, let's do it. This is for Monday's class, should be 7th week, right? Okay, so today we will start Z transform. I think you already know something about it, right? We have some early courses like 310. Yes, 310 where you will have this in 310. So now you think this is kind of review. Alright, and now of course maybe we have something new. So first about the definition. So what is a Z transform? We consider signal x of n. Okay, we consider signal s of n, x of n. Then we perform Z transform. Z transform, we will have capital X of Z, where this capital X of Z equal to summation of all of these X of n times Z to negative n. Alright. Okay, so this is the definition. Z transform. And we consider example. Like x of n equal to 1/2 to the n u of n. Then we have capital X of Z, where the summation of all of these x of n, each one you need to multiply a z to negative n on it. Summation n run from negative to positive infinity, right? This is definition. Now let me plug in the value. This will be summation. Okay, this part is totally same. I just copy it. And the x will be 1/2 to the n times u of n times z to negative n. Alright, we know u of n will be 1 or 0. When it is 0, we don't need those terms, right? The whole thing will be 0. So the summation, we only need n run from 0 to infinity. For these n's, u of n are 1. For other n's, this is 0. Right? Okay, this is 1/2 to the n times z to negative n. Right? U of n is 1. Then I can rewrite it. I combine these two together. It is a 1/2 z to negative 1 to the power n summation. Okay, this is a geometry series. And the result will be, okay, I write one more step. For n equal to 0, it is 1. For n equal to 1, it is 1/2 z to negative 1. For n equal to 2, there will be square of 1/2 times z to negative 1. And then z to negative 1, here's a q, and so on, right? So we have this. So this will be, you can merge them together. There will be 1/1 minus half z to negative 1. Of course, you need a condition. If half z to negative 1 smaller than 1. So we have x of z is a summation of infinite terms. It's a series, geometry series. And the closed form of this infinite summation is this one. In case half z to negative 1 is a number smaller than 1. And here we can consider if this one larger than 1, what will happen? I will see no value can be assigned to x of z. No value. You can't find the value. If it is larger than 1, the power should go to infinity, right? So you have infinite terms, and each term, the value of each term will tend to is larger and larger. So do summation of so many terms, and every term go to infinite. So this is meaningless. When it is 1, is also wrong. Even it equal to 1. Like if this is 1, 1 plus 1 plus 1, that will be infinite. If this is negative 1, if this is negative 1, then it is 1 minus 1, you get 0. Plus 1, you get 1. Minus 1, you get 0. The plus 1, you get 1. So you cannot have a fixed result, right? You add one more term, the value will change. Either 0, either 1, either 0, either 1. You can't have a fixed value. So no value can be assigned to this x of z. Okay, so this is the answer. And this is what happened in generally, not just for this example. So this is a summation of infinite terms. For some value of z, you can have a fixed value for capital X of z. But for some other z, you cannot have the value. Some of z you have value, some of z you cannot have value. As a function of z, you need a range, you need an area. In that range, the summation, we call it converge, right? Converge, you have a fixed value. And in other range, other value of z, this one do not converge, no values. Okay. So we have another thing related with z transform. Also a definition. RC region of convergence. Convergence, yeah, region of convergence, RC of z transform. Of the transform of x of n. That is the z RC equal to a set of z. This one, x of n, z to the n, z to the negative n, for all the integer n's, converge. Alright, it convert. This is RC. So we go back to this example. Continuously. We know x of z will be 1 over 1 minus half z to negative 1 if 1/2 z to negative 1 is smaller than 1. Right? This is our result. Then this is RC. This is RC. RC is half z to negative 1 smaller than 1. Then I try to write these in terms of z. So I times 2 in both sides. I have z to negative 1 smaller than 2. So this is 1 over z, right? 1 over z smaller than 2. So z should be larger than 2, or larger than 1/2. Right? We move z to that side and move 2 to here. So z larger than 1 over 2. As a graph, you can see you have this is 1 over 2, and the outside is magnitude of z larger than 1 over 2. So the RC is the area in the shadow area. If you pick z from this place, then you have x of z. You have a value of the z transform. If you pick a value inside this circle, this one do not have a value. You cannot give a value for it. Okay. This is RC. Okay, so by definition, these just look like this, right? We have a formula like this, and we have RC is defined by this. So definition just like this. Now we want to have more study on it. First of all, it looks very similar with Fourier transform. You see, the transform and DTFT. So x of n, if we perform Z transform, we will have capital X of Z equal to summation x of n Z to negative n, and run from negative to positive infinite. Okay. And if we perform Fourier transform, discrete time Fourier transform, DTFT, then we have capital X of e to the j omega equal to summation of from negative to positive infinite. Here's summation of x of n times e to the negative j omega. Alright, you compare these two. Quite similar, right? This is xn, this is xn. This is power of z, this is sorry, I lost n. This is power of e to the negative j omega. So between these, just one side is z, the other side will be e to the negative j omega. Got it? So you replace the z by e to the negative j omega on x of z, you will have Fourier transform. So this is also the reason why we put e to the j omega here. I do not put the omega as a function of omega. We put the e to the j omega here. Usually when you say a function of some variable, you just put the variable here, right? Now we put the e to the j omega here. Why? Because we want to use the related with the z transform. You just replace z by e to the j omega, you get Fourier transform. Alright, and you can go back. So we can have example x of n. I still use this one. Half to the n u of n. We by DTFT. We have 1 over 1 minus half e to the negative j omega. Remember, we have these. You can check the Fourier transform tables, right? This one by DTFT will get this. So we perform Z transform. It will be, you just replace these by Z. That's it. So this will be capital X of Z equal to 1 minus 1 half z to negative 1. Here's 1. Yeah, this is the x of e to the j omega. You just replace this by z, then you get replace this by z, then you have the z transform. Okay, now let's go to tables. To calculate, to find the z transform just based on the definition, it's something you need a lot of time. It is not hard, just a lot of calculation. You know how to do it, you just keep step by step, you can find the answer. But for those common use signal, people already found the result and list the result in the table. So we can just apply those in the table. Right? I have here. I have this table. I posted this table in Blackboard. So if you go to Blackboard, you can find this table. Yeah, I put it together with the Fourier transform tables. Okay, this is the first table. Table 3.1. Some common Z transform pairs. So we have 3 columns. The most left column, they are the signals, sequence of numbers. Right? Sequence of numbers are digital signals, discrete time signals. So we have delta of n, the impulse, unit impulse, u of n, the unit step, negative u of negative n minus 1. This is also a step function, but it is step down. Let's go back. Let me this what it is. Can I rule full size? Oh, it's very large. I want C. Can I see just item 3? Oh, sorry. It's yeah, it's this one. Yeah, I wanted this RC. Yeah, it's this one. Okay. So what is this one? What is this one? Well, okay. So this one, negative u of negative n minus 1. What it is? You can say you put the value n here. Then negative u of negative n minus 1. N is like negative 3, negative 2, negative 1, 0, 1, 2. Then I plug in negative 3 here, so this will be negative of u of negative 3 minus 1. So this is negative u of 2, right? This is a positive 3 minus 1. Positive 3 minus 1. So it is u of 2. And u of 2 is 1. So this is negative 1. This is negative 1. And this one, this value here, it will be negative u of negative 2 minus 1. So similar, this is a negative u of 1. So it is another negative 1, right? U of 1 is 1. U of 1 is 1. So this is a negative of 1, another negative 1. And this one, this is a negative u of negative 1 minus 1 equal to negative u of, okay, this is 0, right? It's 1 minus 1 is 0. 0 is 1. So here's another 1 with a negative, another negative 1. And then this value it will be negative u of negative 0, right? Here n is 0, negative n is negative 0 minus 1 is equal to negative u of negative 1. So what it is? This is 0, right? U of negative 1 is 0. So here's 0. And you can do similar calculation. You can find this is also 0, this is also 0. Yeah, we can try 2. Negative u of negative 2 minus 1 equal to negative u of negative 3. Right? So it is 0. It is 0. Right? Okay. You see the result is some negative 1, then 0. So look like this. Some negative 1 and 0. And 0. When n is 0, it is 0. When n is 0, it is 0. This is n. Right? This is a negative. This is a. This is the imaginary. I don't know. This is just the column x-axis, right? This is an n, and when n is 0, this is 0, and all the rest are 0. So it looks like this. Look like this. Right? Okay. Then what is the Fourier transform? Okay, it is this one. Right? It is 0. And here's we have an interesting result. You compare second and third, these two rows. They are different signal, but they have same Z transform. Are they same? Totally same, right? However, there are still something different. That's here, the RC. For U of n, RC is you want Z absolute value larger than 1. And for third case, you want absolute value of Z smaller than 1. Okay. So this is the difference between them. Okay, then we have more more signals. We have one is dirt, second is U, third one is a reverse side of U, then the fourth is dirt, shifted dirt. Right? You compare 1 and 4. 1 is U of dirt of N. Right? It's dirt. It's an impulse. And the 4 is a dirt of M minus M. So this is a shifted of dirt. Shifted by M. Right? Dirt of N minus M. It looks like this. This is N. This is M is here. M is here. This is N equal to M. Here M is for time. Here this is N. N is for time, and M is a fixed number, shifted by M. And all the rest will be zeros. Right? So this is dirt. Shifted dirt. Shifted dirt in by Z transform, we have Z to negative M, and our C, or Z except 0 for positive N, positive M, or infinite for negative M. Right? So this is a Z value cannot be 0 or cannot be infinite. This is second one, fourth one, and the fifth and sixth. They are also similar relation like 2 and 3, right? They are different signals. One is for positive N, you can have value. The other is for negative N, you can have value. And they have same Z transform. Right? You see, they are same. Z transform same, but they have different ROC. For the fifth row, the ROC is larger than Z larger than, or the absolute value of Z larger than A absolute value. So actually this is a circle, right? This is a circle. You can see. Let me write here. Z larger than some A. There will be, here's A, and outside. This is outside. And the Z smaller than A, there will be, of course, it will be inside circle. Here's 1 over A. Yeah. So this is the RC of 1 over, which one? This one. RC of A to the N times U of M. And also it is this is RC. This is a transform. This is signal. And 6 is another signal. But the transform functions are same. However, the RC are different. Right? These two, they have different RC. Yeah. One is larger than value, the other is smaller than the value. Okay. So this is 5 and 6. And the 7s and the 8s, they also pairs. These two are also pairs. Alright, they also pairs. And then we have cosine. This cosine times U of N, that means the cosine will start from N equal to 0. For negative N, this signal is 0, keeping to be 0, so no values. After N, go to positive side, start from N equal to 0. After that, then when N go to positive side, then you have a cosine. Similar with sine. Okay. Then the function is here. Both are the fraction of two polynomials on the z to negative 1. And this cosine of omega 0, it is a constant because omega 0 is a given constant. Right? So this is cosine is also constant, and this is sine is also constant. And then we have 11 and 12. This is a cosine or sine, but before that you multiply a power of r on it. Then what will happen in the after the z transform? It will be this one. It will be this one. All right. And of course you also need the RC. ERC. Okay. The last one, a to the n. This a to the n, we have only finite terms. We can compare this with the previous one. Yeah, fifth. You see the fifth. Fifth is an, u of n. So this fifth one, you can write in this way. So an, a to the n, u of n. Actually, this is an if n is positive or 0, and 0 if n is smaller than 0. You can write in this way or that way, the same thing. These two are same thing. And now you compare the table. Here we have this one. Here we have an, right? An. This an. I see this is a. I give a name for. Let me copy it. I copy these in my paper. Alright, and go to that side is 1 minus a to the n z to the negative n over 1 minus a z to negative 1. Okay. It's here. I copy. For this signal, by z transform, we will have this one. We will have this one. And here, suppose like I write this as x of n, omega of n, w of n. Then this will be w, capital W of z. Will be this. Will be this. How can we get this? You know, for example, we have another one. This one go to 1 over 1 minus a times z to negative 1, right? The difference is here. And you compare these two, you know, this is for all the n, you have a of n. This is a to n only when n runs from 0 to n minus 1, right? You let this capital N go to infinite, you will have previous one. And here is also, you let capital N go to infinite, this will tend to be 0. A to the n will go to 0. Suppose a smaller than 1. This one will same with that. These two will be same. Alright. But in generally, we do not have this requirement. So these two, the limit of this might be not that one for some other n's. To get this one, you can think capital W of z. By definition, there will be summation of w of n z to negative n. But now w of n is just a to the n. For n run from 0 to n minus 1. For all the other n, it is 0. So the summation, we only need this term will be fine, right? For all the other n's, this is 0. So we will keep this will be fine. And okay, Wn is a to the n, this is z to negative n, and this is geometry series again, but we have finite terms, so it's 1 minus a n z to negative n over 1 minus a z to negative 1. That's it. Same with that. Got it? From here to here. Actually, this formula, yeah, I can go over that formula again. We have this formula before, right? We have this formula. 1 plus a squared up till a to some n there will be 1 minus a to the n minus a plus 1 over 1 minus a. We have this formula. For any a, you can have this formula. To prove it, you just check 1 minus a times 1 plus a n. This will be 1 times all of these, and minus a times all of them. So it's a, like this, a squared until a to the n plus 1. Okay. Then all these terms they cancel, the plus and the minus. So the result is 1 minus, cancel to here, a to the n, and keep 1 to the n minus plus 1, a to the plus 1. So you times these two together, you get this one. Then you divided these to the other side, you can have, you get this one, right? You get this one. Okay. Alright, so this is a table. That's me. Table. Which table? This table. Yeah, this table. Okay. Alright, this is the first table. And the second table. Now we go to the second table. Second table are some properties of Z transform. Here we have totally 9 properties. You go to the textbook. In textbook, they explain these items one by one, right? One by one. So here I just introduce you this table. When you want to use something, you go to the table, you can have that, right? You can use the result in the table. Here the first one is a linear feature. When you combine x1 and x2 linearly, so a times x1 plus b times x2, then perform Z transform, it is also a times x1 plus b times x2. Same way. The only difference is now it's a function on Z, and the previous one is a signal on time n. Right? So this is the first one. And of course, we also need to consider the RC. What is RC after you do this combination, do this summation? That will be might be larger. It will contains Rx1 intersection with Rx2. Alright. Yeah. So yeah, things like if you have two, like if xn go to x1 go to capital X1 Z by Z transform, and x2 of n by Z transform, I have x2 of Z, and with RC R1, this is a RC R2, then I don't know what it is. For example, this is a R1, this is a R2, then the intersection will be this. This part is a R1 intersection with R2. Yeah. Okay, so it is this one, R1, R2, right? R1, R2. So ax1 of n plus b x2 of n will go to a capital X1 of Z plus b capital X2 of Z, and this RC do not contain this part. No R1 contain, sorry, I'm confused. Yeah, we need this part. Contain RC contain R1 intersection with R2. Am I good? Yeah, so like this. Right. And we have more terms. And the second one is a shift. X of m minus n0, that is a shift of a signal. Right? This is a shift of x. Then as a z domain, after you do the transform, it is still capital X of z, but before that you need to multiply a constant. This another function multiplied by another function z to negative n0. The n0 is a distance in your shift. How many distance did you shift the signal? You shift by n0, and here's a negative n0 here. And what is RC? Here's a RC should be same, almost same, but depending on n0. If n0 is, because this one maybe cause if you let z equal to 0, maybe you have 1 over 0, right? So you have to remove the original point 0, right? Maybe you need to delete this original point. And if z is positive, maybe you need to add original point. All right, yeah. And also you consider the infinite point, the infinite point of z. This is RC. The second case, when you shift. And the third one, it times the power in front of the signal. Signal is x of n. I times z0. Z0 is a constant. The power of the constant. I times this in front of x. Then in z domain, you need to change z by z over z0. Then you have the z transform. And at the same time, for the RC, you need to times z0 on the RC of x. So this is the third one. And also we have the fourth one, the fifth one, the sixth, and the seventh. So I suggest you go over all of them, read them, try to understand them, and if you want, you can copy 1 or 2 times. Then you can have some sense about these properties. Try to understand them, try to remember them. At least you have some feature. So when you need to use them, you know how to find it, where it is, right? Yeah. You maybe you do not remember it, but you can have some sense about it. And among these, we have several things are important. Let me see. One is the convolution one. Yeah, last one. Convolution. You see, when you have 2 signals, you do convolution in the time domain. Then you perform z transform. In the z domain, you will have a multiplication. Right? The multiplication. The capital X1 times capital X2. So the z transform of first signal times the z transform of second signal. That gives us the, in time domain, you will go back to time domain, there will be a convolution of x1 and x2. So this is a very important feature. For Fourier transform, we have similar thing, right? For Fourier transform, we have similar thing. Now the z transform, we still have this kind of feature. Okay, this is a nice one. And for our work, we are working on the signal processing, right? On signals, on systems. The most important feature here are the second one and the last one. Second one is shift. When you have a shift in time domain, there will be in time domain is a shift. Then in the z domain, you need to multiply a z to negative n0. And the last one is a convolution in time domain related with the multiplication in the transfer domain, z domain. Right? So these 2 things we use a lot. I can use an example. Suppose I have a signal y of n minus 1/2 y of n minus 2 equal to equal to dirt of n. Suppose this. Then what is y of n? What is y of n? I perform Z transform. Y go to capital Y and minus half. Okay, this is y with a shift by 2, right? Y shifted by 2. Y shifted by 2. Then you use this. Oh, sorry. I forget this. Sorry. Yeah. I need to go to here. Yeah. Example. We consider a system with the data of n as input. Right. This side is the input. The data of n is the input. This is the equation, difference equation of the system. Right. With this equation, we want to find y of n. What is y of n? Now we perform Z transform. So y of n go to capital Y of z, and half is still half. This y times n into 1. Okay, y of n minus 1 will go to capital Y of z times z to negative 1. Yeah, this is the based on this feature. So here, shift by 1. Then you times power of z on it. Right? Here shift, and this n minus 1 here is negative 1, z to negative 1. Alright, we have this one. Then the other side is equal to dirt. What is the dirt? Dirt is, we have the table here. Dirt is 1. You see, dirt by transform, Z transform, you get 1. So this is 1. Okay, then you can have y of z times 1 minus half z to negative 1 equal to 1. Then you can have y of z equal to 1 over 1 minus half z to negative 1. Right. So you can have the Z transform of y. And also then we go back, right? We'll go back. The inverse transform. We have y of n equal to 1/2 to the n u of n. Right? We have this one. See? Okay. So this is we have a shift here, we have a multiplication by this z to negative 1 here. Right? Okay. This is the table 2. Table 2. Alright. So in the textbook, these two tables, they explain it almost item by item. So it covered several sections. I think at least 2 sections. After the class, I suggest you read those part. Read those part. It is not necessary to read all the proof, but some of the proof, some of the calculation is quite simple. So you can still read it. It won't cost you too many times. All right. Yeah. And here I just introduce these 2 tables to you. When you want to use it, you know where to find them. Like you have, for example, you have n times some numbers power. Then you go to here, right? If you have this, then you know, okay, I can use the table directly. I can find the transform of that signal. Right? So if you're familiar with this table, very good. Very good. And read that textbook, that part of the textbook, that make you understand why do we have this. So we have 2 sides, right? One side is understand why we can have this. The other side is you're familiar with it, and then when you need to use them, you can find them quickly, right? Find them quickly. So we have these 2 tables. All right. Actually, in this semester, all the exams, you are take it online, so you can have this table with you, right? Very convenient. And even in previous semesters in the on-campus class, I also ask you to print these and bring these tables with you for all the exams. Okay, so but whatever, this one is very useful. This table is very useful. This is similar with the Fourier transform. You can see, if you want, you can compare this with the Fourier transform. You can find most of them, they are similar with almost the same with the Fourier transform. But we do not have those infinite summations. Remember, I think for here I have all the table. This is a Fourier transform, right? This is Fourier transform table. I also have Fourier transform. Yeah, this is Fourier transform. You can compare with the like this one. You have an infinite value, summation of infinite terms, right? Summation, and when signal is u of n, here you have summation of infinite terms. This is for Fourier transform, and for the Z transform, we do not have those infinite summations. Actually, I have just mentioned, I said, when you replace Z by Z to negative E, let me see which part. I have an example. I said you can replace Z by E to negative. You get this one. Yeah, I have example here, right? This one, if you replace this by Z, you can get this one. This happen only if both Z transform and Fourier transform, they are how to say. Okay, then I need to explain something about the RC. After that, we can explain in which case you can replace Z by this one to get the other side. Not always. Here we have the example. You just check the table. Like this U of n. In Z transform, you only have one term. And in Fourier transform, U of n, this is U of n. You will have, you see, one fraction plus infinite terms, a summation with infinite terms. This is U of n's Fourier transform, right? So that's different way the Z transform. You see, Z transform, you only have a fraction, right? 1 over 1 minus Z to negative 1. Only have this fraction. Do not contain all those infinite terms. So this gives us something. When you calculate, you use Z transform, you can make things simple. When you use Z transform, you can make things simple. Yeah, all the previous homeworks. So when I give the homework, I suppose you can use Fourier transform to solve it. But now you know you can use Z. You can also use Z transform. Use Z transform to solve it. All right. Okay. What else I want to mention? Alright, I think that will be all for today. So today we only have two things. One is about the definition of Z transform, right? Definition of the Z transform. Of course, also contain the RC. What is RC? When you have Z transform, at the same time, you also need RC. And the second thing is introduce you the tables. We have two tables, and they contain the most common used signals, and also contain the most useful theorems about the Z transform. So you need to use these time again. Alright, so that's all for today, and I will have some homeworks, so you can check the Blackboard, find the homeworks. Alright, see you next time. That's all for today. Bye bye.